All right, going into number 8, let me remind you, if you do not show your work, you will get 0 credit. I do not care. I do not care if the answer is right. This is about showing your work and showing your own thinking. So if you don't do that, you don't get any points at all. 0. Show your work or no points. So number 8. What is the frequency of light that has a wavelength of 310 nanometers? Okay, before I even get into the actual math, let me point out that the question has given me data, 310 nanometers, shows 2 significant figures. Right? That trailing zero is not significant because there is no decimal in the number. If it was 310 with a decimal at the end, that would make it 3 significant figures, but there is no decimal, so that's 2 significant figures. So why is that important? Whenever I record my final answer, I need to record it with 2 significant figures. All right, so I'm going to be calculating frequency based on wavelength. And so I'm going to use my equation, C is equal to lambda nu, and I'm going to rearrange that equation, right, algebraically, to solve for frequency. Why? Because the question's asking me to solve for frequency. So, after I rearrange, I have frequency is equal to speed of light divided by wavelength, right? C over lambda. Well, the speed of light is a constant, right? 3.0 times 10 to the 8th meters per second. And the question actually gives you wavelength, 310 nanometers. Now, there is something that you need to take into consideration here. First off, the speed of light is indicated in terms of meters per second, but the wavelength that the question gives you is communicated in nanometers. That means if I were to simply plug in 310 nanometers into this equation, the units would not cancel sufficiently, they wouldn't cancel appropriately, so that the units for my frequency and my final answer would be hertz, or 1 over seconds. The units would not cancel appropriately. So what I have to do is I have to convert nanometers into meters. Well, you can do that pretty darn simply by replacing the n in nano by times 10 to the times 10 to 9th power. Okay, because it actually takes it actually takes 10 to the 9th nanometers to add up to 1 meter. So we can plug in times 10 to the negative 9 down here on the denominator. So I actually have 310 times 10 to the negative 9 meters. Now, once I've done that, I'll be dividing a meters per second by meters. That will actually allow the meters to cancel, and I'll just have 1 over seconds for my unit, which is the unit of frequency, so that's all good. Now, once I replace that nano with the times 10 to the negative 9, I'm going to have to deal with the exponents. Now, hopefully you remember the rule about dealing with exponents in calculations. If you are dividing 2 numbers, which I am here, if you're dividing 2 numbers that have exponents, you simply subtract the exponent in the denominator from the exponent in the numerator, and that's it. It gets a little bit tricky. Students often forget that it's a subtraction. So for the exponent in my answer, I actually need to carry out 8, right? 8 on the numerator, subtract, right, because I'm dividing here, 8 negative 9, right? So that's the negative 9. So it's 8 minus negative 9, which is equal to positive 17. So when I plug these values into my calculator, I get this big old long value, 0.009677419 times 10 to the 17th 1 over seconds, which is also known as a hertz, right? The exact same thing. So I'm going to start calling this a hertz. Now, this exponent looking good, but this value not looking good. I need to use the appropriate number of significant figures, which is 2. Right? So that would bring me to this 6 right here, the second significant figure. Well, the 7 right behind it tells me that I should round that up, so I'm going to end up with a 9.7. That's all I'm going to report. But I also need to put this into proper scientific notation. So that means I have to move this decimal 3 places. So it's 9.7. Right? Remember, for scientific notation, the value that you report actually needs to be between 1 and 10. So this is between 1 and 10. Good to go. But I did move decimal 3 places, so I'm going to have to change the exponent by 3. And you guys remember my trick, which is as a result of moving the decimal in this figure right here, in this value, from this value to 9.7, this number actually got bigger. Okay, is that fair enough? This is way, way less than 1. This is almost 10. So I think it's pretty clear that this number got bigger to become this number. Well, that's a change, right? It got bigger, which is actually not allowed. I'm not allowed to change the value of my answer, because that means that it wouldn't be the result of this calculation. So in order to balance out the fact that this part value got bigger, the exponent has to get smaller, right? It balances this out. And so the reason that's important for me is because that actually tells me conceptually, should I make this 3 smaller than 17 or 3 bigger than 17, which is a common confusion that students have. And so in this situation, I need to make it smaller by 3. So my final answer is 9.7 times 10 to the 14th hertz.